The topic of this lecture is diagonalization of symmetric matrices. And suddenly, why symmetric matrices appear in the topic of diagonalization? Why? The answer is very simple. See the question, what is special about these symmetric matrices, right? You know what is a symmetric matrix? A matrix is called symmetric. A square matrix is called a symmetric matrix whenever it is equal to its transpose, right? That is A equal to A transpose, okay? And here why we are studying these symmetric matrices in the context of diagonalizability. What is so special about them? So this is a special answer. They are always diagonalizable. Symmetric matrices are always diagonalizable, right? So far you studied that whenever a matrix capital A has distinct eigenvalues, then it is always diagonalizable. You can read it here. It is the first point. Matrix having distinct eigenvalues is always diagonalizable. Distinct eigenvalues implies diagonalizability. Okay, good. Second point, but if a matrix has repeated eigenvalues, then it may or may not be diagonalizable. Anything can happen. It may be diagonalizable, it may not be diagonalizable. It will depend actually on the number of linearly independent eigenvectors that will be furnished by those eigenvalue eigenvectors equation, that is A minus lambda I times V equal to 0. To do that, after finding the eigenvalues of matrix, you then you calculate eigenvectors, right? Okay, so repeated eigenvalues doesn't conclude anything actually, right? Now read out this next question. So the next question comes into our mind, that is every matrix with the distinct eigenvalues diagonalizable in real field? And please pay attention, this is a new word for all of you. What is a real field? A real field means when you are dealing with real numbers only. It means that you are in the universe of real numbers. Of course, we assume that we are in the universe of real numbers. So far, you assume that since you are just in first semester course, but in third semester course and onwards, you will be assuming that you live in a world of complex numbers, because at that moment, at that time, after 1 year, you will be accepting numbers like eta and 2 eta and 1 plus eta, etc., right? In this first semester course, you will not be going to accept complex numbers in your world, right? So, real field means real world. I mean, this mathematical real world is called real field. This is the simplest definition of a field I can give to you. Since we are BTech students, and these definitions are meant for pure mathematics students, so you can assume that real field means the real mathematical world. A mathematical world where only real numbers are allowed. That's it. So the question was, is every matrix with distinct eigenvalues diagonalizable in real field? The answer is surprisingly no. Right? So the first point was saying that the matrix is diagonalizable if it has distinct eigenvalues, but this question has a negative answer. No. Sometimes a matrix may have distinct eigenvalues, but it cannot be diagonalizable in real field. Right? See this matrix. If you write its characteristic equation, then it will be lambda square plus 1 equal to 0. This is very simple. How to write a characteristic equation of a 2 cross 2 matrix, I have already taught you. When you solve it, it will give you lambda square equal to minus 1. And then you take a square root. And whenever you take a square root of minus 1, then you put plus minus sign here, because this is a quadratic equation. And a quadratic equation always give two roots. Sometimes repeated roots, but if it gives distinct roots, then they should be two number, right? Then it gives you lambda equal to plus minus eta. You know that what is eta? Eta is the square root of minus 1. Now see that the first eigenvalue is eta and the second is minus eta. You can see that these are distinct eigenvalues. Yes, of course they are distinct, but unfortunately they are not acceptable in the world of real mathematics. The world of mathematics, which is related to a first year student, I mean the real field, right? So you are dwelling inside a real field and you are seeing some numbers like this. So these numbers are appearing like aliens to you, like for all of us who are living on this earth. What should I say? An object which looks unfamiliar to us is called an alien. right? And of course we have seen aliens in movies also, right? They are some different structure, not similar to humans, of course, so we call them aliens, right? And if we consider ourselves as a humans of universe, I mean, if universe is considered as our home, then aliens are our siblings, right? And we'll accept them, of course. Okay, since you are living on the earth and the person from other planet is called alien, right? Same is happening here. You are living in a mathematics real world, and you are watching these iota and minus iota, and you're saying, what are these numbers? Iota and minus iota, what is the square root of -1? You don't know how to find the square root of a negative number, right? So you have to reject them. You cannot accept them, in spite of the fact that they are distinct, right? So eigenvalues are distinct, but unfortunately, complex eigenvalues are not acceptable in the real field, right? And hence, this matrix is not diagonalizable. Are you getting my point? So the answer to this question, if someone asks you that every matrix with distinct eigenvalues is diagonalizable in real field, so you said no. But if it changes his question, that is every matrix with a distinct eigenvalue diagonalizable in a complex field, the answer is yes. Of course, these numbers will be accepted in complex field, right? If you see this mathematical world as a wider space, right, and the space of real numbers, then of course you will be going to accept them. In that case, they diagonalize. And this is a remark written here. So in complex field, this matrix is diagonalizable, because in complex field, in the world of complex number, when you allow yourself to dwell in the world of complex numbers, then you will be going to accept them very easily, because you are familiar with the complex numbers, right? And then you will say that yes, these eigenvalues are distinct, hence they are diagonalizable, hence the matrix is diagonalizable, right? But for now, for the moment, we will say that this matrix is non-diagonalizable, because today we are living in the world of real numbers, right? We are restricting our study of this matrix theory to real numbers only, right? Everything you are studying in this unit number 1 is acceptable unless and until it is not a complex number, right? So at this point, you will be going to disregard these complex numbers. We are saying that what are these rubbish numbers? We are not going to accept them. These are complex numbers. They are not allowed to enter in our real mathematics world. Right? So hence this matrix is not diagonalizable, because it is not having any eigenvalue. Actually, it is not having any real eigenvalue. So we cannot find real eigenvectors, and that's why this matrix cannot be diagonalizable. Right? Now, to proceed further, the next question comes into our mind is that, does it mean that a symmetric matrix always has real eigenvalues? Right? Because I have already written here, what is a good thing about symmetric matrices? The good thing is that they are always diagonalizable, right? Now you know that not every matrix is diagonalizable in real field, right? What will happen if a symmetric matrix will be having complex eigenvalues, right? So this is a question. And this is a question that, does it mean that a symmetric matrix always has real eigenvalues? So the answer is yes. A symmetric matrix always possesses real eigenvalues, and the reason can be given. This reason can be given, though this is not the complete reason, but I am just trying to give you justification for this yes, right? By taking a 2 cross 2 matrix. However, this is not the actual proof, right? So if you take a 2 cross 2 matrix, consider a 2 cross 2 matrix and let it be a symmetric matrix, and you all know how to write a symmetric matrix. If I write A here and I write B here, and since it is a symmetric matrix, then this element should be B only. There is no choice to write any other element at this place. And here you can write C. You can see that this is a symmetric matrix, right? It is symmetric. You know that this matrix is symmetric. And these all A, B, C, D are real numbers. A, B, C belong to real numbers. Since you are dwelling inside the real field, you all know that we are in the real field now. Right? Complex numbers are not allowed at the moment. Okay. Now just try to write the characteristic equation of this characteristic. equation, and that is lambda square minus trace of this matrix is A plus C times lambda, then determinant of this matrix is AC minus BT, and AC minus B square, sorry, AC minus B square equal to 0. So this is a characteristic equation. And since it's a quadratic equation, and you know that for a quadratic equation, if the discriminant, you know that what is discriminant for quadratic equation? You know that finding the discriminant of this
minus
B square minus 4AC.
B square minus 4AC.
Yeah, B square minus 4AC. And what is the speciality about discriminant? What information does? If discriminant is positive, then the roots are real and unequal, right? Discriminant is 0, then roots are repeated, right? And discriminant is negative, then roots are imaginary, right? Even at that point in class 11th, I think, greater than or equal to 0, then real roots only. Distinct and repeated cannot be said unless and until we know that they are greater than 0 or equal to 0. So I have taken actually 3 conditions. You are saying only 2 conditions in one. Greater than or equal to 0 is having 2 conditions in one condition actually. So finding discriminant, that is capital D, and that is B square minus 4AC. Let me write it, B square minus 4 capital A into capital C. And what is B? This is my B. The coefficient of lambda is called B. So that will give you A plus C whole square, because minus is there and the square of minus is plus. And minus 4 times capital A is 1 actually. Capital C is AC minus B whole square. Right? Let me solve it. If I open it, it will be giving A square plus C square plus 2AC minus no AC. I think I have put a square at the wrong place actually. This should be minus B square like this. Now it's fine. Okay, fine. And that will give me plus 2AC minus 4AC plus 4B square. And simplifying it further, it will be having A square plus C square minus 2AC plus 4B square. And why don't we write it as A minus C whole square? Then you can see that this is a formula of A minus C whole square and plus 4B square, right? And since the final value of the discriminant, this is a positive number, it cannot be negative, it may be 0. If you put A equal to C, then it may be 0, right? And this is also a non-negative number. Both these numbers are non-negative numbers, right? Non-negative. It is sure that they will be non-negative. They may be positive or 0, but they cannot be negative, right? Non-negative. Both are non-negative. Right? It means that D can never be less than, it can never be, I will cut it like this. D can never be negative. This is clear to all of you, right? And which implies that this quadratic equation cannot have imaginary roots or complex roots, which implies that real roots, real roots are of course real roots. Yeah, so we are right. Real roots, there will be real roots. They may be equal or unequal, but complex roots are not possible. This implies that lambda is real, right? And which proves that eigenvalues are real. Lambda, what is lambda? Lambda is eigenvalue, which proves this fact. And I have proved this fact for a 2 cross 2 matrix. For the matrices of higher order, the actual proof is something else, right? I'm not going for that. I'm just trying to convince you why I wrote this. Yes, okay. So here another good thing about symmetric matrices, that they will not allow complex eigenvalues, okay, into a domain. If you find the eigenvalues of a symmetric matrix, then eigenvalues will always be real, right? This is a guarantee. There is a guarantee that symmetric matrices always have a real eigenvalues. Okay. Now I'm going to question. See, as A and find the modal matrix capital P such that P inverse AP is diagonal, right? This is a question. We have to give P also, and this the question is very similar to the earlier one. We have already done such type of questions, right? Okay. Now there is an observation. Is P inverse AP equal to DIAG lambda 1 comma lambda 2? This is a question to you. Is it happening there that P inverse AP becomes the DIAG? However, this is true. I have taught you that this is always true, right? Okay. And second is what modification in the eigenvectors v1 and v2 say be done to get inverse AP equal to DIAG lambda 1 comma lambda 2. So these two questions are actually eye openers, and these are very important before studying any theory about the diagonalizability of symmetric matrices, right? Why this symmetric matrices is studied alone like this, like in this topic. Okay, I'm going to the solution, and please pay attention that I am not going to do anything new. Whatever we have done so far, I'm going to do the same things, right? I'll be starting with the characteristic equation as I always start. Characteristic equation, and you all know that that is det determinant of a minus lambda I equal to 0. However, this formula is just a formal formula. We don't actually use this formula because this will take too much time. We use this shortcut trick, lambda square minus trace of a. What is trace of a? You can see that trace of a is 4 plus 1 is 5, and that will give you 5 lambda, and plus a determinant of a, and determinant is 4 minus 4, that is 0. So determinant is 0 is equal to 0. So this is a nice way to write a characteristic equation, right? And if you factorize it, then you will be taking common lambda, and inside bracket you will be having lambda minus 5 equal to 0, and that gives you actually two eigenvalues, and both of them are distinct. First is lambda 1 equal to 0, and second is lambda 2 equal to 5, and both are distinct. So first thing is that distinct eigenvalues are always good to have, because there is no tension to get two or three eigenvectors from just one eigenvalue, right? You will be observing this in the next section, that actually repeated eigenvalues are not always good to handle at this age between 18 to 20, right? So distinct eigenvalues. Now I am going to the first step. My first step, let me call it number 1. For the first eigenvalue lambda 1 equal to 0, calculation goes like this: a minus lambda 1 I, and lambda 1 is 0, times v1 equal to 0, right? And then you subtract the this number 0 number from the diagonal of this original matrix. That gives you 4 2 2 1, and for v1 you write xy, and the right hand side is actually 0 vector, so you replace it by 0 0, and then you observe that this is a homogeneous system, and then you always go for applying the row operation to get elements below this principal diagonal to 0 element. So the operation you will be using should be R2 implies twice of R2 minus R1. Is it right? That gives you 4 2 2 1, but at this moment I just remember one thing, what I used to do in few classes. I just try to write the eigenvector directly, and I'm just skipping the calculation. I will show you how to write it directly. I know that answer will be something like this. See how I write the answer directly without actually doing anything. The answer will be 2 and -4. No. This is A, B, C, D. A, B, C, D. I will write it here. The answer will be B and lambda minus A. Lambda is 0, so that should be -4. 2 minus 4. Am I right? Yeah, this is the answer directly. And the trick is this trick. See this secret formula. This is a formula for A or lambda or eigenvalue lambda of square matrix A, B, C, D, eigenvector is V equal to, write B here and lambda minus A. This is a shortcut trick to write eigenvector without actually doing any calculation. Right, so I will just box it. Right, and this will be your right, and that's why I've used the formula. I know that this is A, and not just this one actually. Original matrix. Where is my A? This is my A, and this is my B. So using this formula, B, I wrote B here, and lambda minus A. Lambda was my 0. 0 minus A was gave me -4. Right, this is a shortcut trick. Let me complete the calculation also. Right, and applying this row operation, we will get, sorry, this will be 0 0 actually. 0 0 xy 0 0. Right, so that gives you an equation that is 4x plus 2y equal to 0. You have only one equation, and you have to assume one variable as arbitrary. Assume n minus r. N is number of variables is 2. Rank is 1. You can see that the rank of this matrix is 1. That gives you 1. Assume one variable as arbitrary. And when you assume one variable as arbitrary, you assume y equal to k. That y, oh sorry, y equal to k, then x will be minus k upon 2, right? And if you I'll rub this. If you write the eigenvector v1 is equal to, therefore v1 is equal to, the value of x is minus k by 2, and this will be k. And you always know that you can take common, minus k by 2 can be taken common. Then inside bracket you will be having 1 here, and here minus 2. Am I right? Yeah. Okay. And this is what I wrote directly. I actually wrote to see. If you use a direct calculation, I'm writing it here. Writing it here for this question. For this question, you have a is equal to, what was a? A was 4 2 2 1 4 2 2 1, and for lambda 1 equal to 0, this formula will give you v1 equal to, what is b? B is 2, and 0 minus a will give you -4. And you can see that you can always take 2 common from here, and if you take 2 common from here, then you will get 2 common, and inside bracket will be having 1 and -2. You see that this is the same this one. You're getting my point? So this trick works very well. Yeah, of course, we can take any number common. Any k can be taken common. This is also correct. Even if you take only k common, even this is also correct. If you take k common, somebody will be getting like this, -1 by 2 and 1. This is also correct. If someone take k by 2 common, then he will be getting -1 and -1 and 2. This is also correct. Everything is correct. Every vector, every eigenvector is correct, no matter whatever value you take common, right? Okay, so we are just writing one of them, and right, I want to erase this actually, not box this. Okay, fine. So this is the eigenvector. Therefore 1 minus 2 is the first eigenvector, which could be obtained directly using this formula. And now for the second part, I will use this shortcut formula to save my time. Time is precious. Second, for lambda 2 equal to, what is the second eigenvector? 5. I'm writing the direct formula, using direct formula. Please try to use the direct formula. What is B? See, what is B? B is 2, A is 4, right? B is 2, A is 4. So here you write B and lambda 5 minus 4, right? And that gives you 2, 1. So this is the second eigenvector. I have used this shortcut formula. This one. You have two eigenvectors, and the first part was asking you to find the modal matrix P. Yeah, yes, Shivam Verma. Only for 2 cross 2. For 3 cross 3, there is no shortcut. Hence, P is equal to, P is constructed by using the first and second eigenvectors, putting in column. The first eigenvector was 1 minus 2, 1 minus 2, and second is 2, 1. Is modal matrix. But now comes an important question, because the role of modal, what is the role of modal matrix? The role of modal matrix is this one. A modal matrix is a kind of mediator, right, which helps us to get that D, diagonal matrix D, right? Modal matrix is something which meets us in our journey towards the search of diagonal matrix D, right? So that is kind of mediator. Okay. Now the question arises whether this modal matrix P, we are claiming that this is a modal matrix. This one is a modal. We are claiming that this is a modal matrix. Actually, this is claiming that it's a modal matrix. But is it solving our purpose? Is it able to get that capital D by using this formula? Inverse AB should be equal to this formula. Sorry, inverse AB should be equal to DIAG lambda 1 lambda 2. Right now we want to see that. This is also an eigenvector. I'm just completing it. Okay, fine. Now comes the first part. First part is A part. Read out the first part. Sorry, I should remove this thing actually, because actually this inverse, I know that this will not be a diagonal, so I'm just removing it. Okay, and the modal matrix P, I'm just changing the language, consisting of which is non-singular, just which is non-singular, because I know that the answer for the first part is no. This is not going to happen this time. See, answer for part A, right? Now I'm going to what I'm going to do. I have already claimed that, though my claim is not correct. I have already claimed that this is the modal matrix. It looks like modal matrix, and of course it is non-singular. If you find the determinant of this matrix, that will be non-zero. Of course, V1 and V2 were the correct eigenvectors. We haven't committed any error in our calculation, so it appears like this is modal matrix. Let us find its inverse. Inverse, to find inverse of a 2 cross 2 matrix, we have a very shortcut trick. We just switch these diagonal elements with one another. So you will be getting one here and one here, right, by switching them. And you just change the sign of these elements. It will be minus 2, it will be plus 2. But what is left, you divide it by finding the determinant of this. So 1 minus minus 4, that will give you. So this is a P inverse. Are you getting my point? Okay, then now I want to see that D P inverse A D is equal to what? I think you will be able to get diagonal. Now it's looking like we will be getting D minus 2, 1. This is P inverse. And what is A? A was A 4 to 2, 1. 4 to 2, 1. And what was P? 1, 2, minus 2, 1. multiply them. 1 minus 2, 2, 1. And if you multiply these last two matrices, that will be 4, 0, 0. 8 plus 2 is 10. 2 minus 2 is 0. And 4 plus 1 is 5 actually. Right. Okay. I'll multiply these two also. 0. Okay. And 10 minus 10 is also 0. I think we are getting the correct answer. 0, 0. This is also 0. And 20 plus 25. Right. And since this 5 is waiting outside to divide each of the entries of this matrix by 5, 0, 0, 0, 5. So in fact, we are getting the that EIAG and 0, 5. You can see that these are diagonal numbers. Of course, they are lambda 1 and lambda 2. So I was wrong in prediction. Actually, this is actually giving the correct answer. So no modification is required. This is lambda 1, lambda 2. You can see that your lambda 1 was 0 and lambda 2 was 5. Nothing special is happening out here. I think this modification is not required at this point. The modification is required only when in the case of repeated eigenvalue. Sometimes I don't want to waste my logic. P transpose. P transpose. P transpose is transpose of P. I will write it here. Where P to the power T is transpose of P. Right? So this is the question now, and now comes the. Is it clear to all of you the first part? We're actually getting P inverse AP equal to. It means that this mediator matrix P is working here, of course. Fine. Now the second question is something else. It is asking you to get DIAG lambda 1 lambda 2 by changing this formula. You see this formula. This is P transpose. This is not P inverse, right? So this is the next target. Those who hate to find inverse, and everybody hates to find the inverse at this stage, as compared to finding the transpose of a matrix. I will ask to Adid, Mr. Adid.
Yes, sir.
So what is your favorite task to find a matrix or transpose of a matrix?
Transpose.
Transpose, of course. You will be preferring to find the transpose. Of course, and everybody does. Me too. And for a matrix of higher order like 3 cross 3, 5, 4 cross 4, 5 cross 5, everybody will clearly say that, sir, we will be going to find the transpose, because finding transpose is easy. But and of course, finding inverse is very time-taking process. Is it correct? So we are going to do some modification in V1 and V2. Please. I'm trying to tell you why we are doing this. Actually, we are just trying to escape the process of finding inverse. That is very boring process. Finding inverse, finding adjoint and then dividing by determinant, that can be avoided, but that can only be avoided when you are dealing with a symmetric matrix. That's why symmetric matrices are very interesting. Right? They give you a scope to avoid finding the inverse of modal matrix P. You can just find the transpose, and the great thing is that this formula still holds. Just changing P inverse by P transpose. Are you getting my point, Adit?
Yes, sir.
But a modification has to be done somewhere, and those modifications will be done on V1 and V2 if you want to save your time, because finding transpose actually saves time as compared to finding inverse, right? So the question is already done. There is no problem in the question, but for the students who are lazy in finding inverse, they should go for this point number B. Now I'm going to solve this part B for the students who hate finding inverse. Right? Okay. Now part number B. C. It was asking for the modification in V1 and V2. So I will just pick cut V1 V2. I know that this V1, where is my V1? This is my V1, and this is my V2. Where is my V2? This is my V2. I will just copy these V1 and V2, and since copying from your own work is not cheating, I am just copying them. The first one was V1 equal to 1 and minus 2, and the second was, what was the second? 2, 1. I'm going to modify them such that all of you will be avoiding to find the inverse of matrix, because everybody will love to find transpose as compared to inverse. What modification could be done? See, please pay attention. First observe that, this is a good observation. Observe that if you multiply V1 with the transpose of V2, this is an observation. And this is not just a coincidence, it will happen every time. See, sorry, I should write it like this way, transpose of this thing, transpose of first and second. V1 transpose 1 minus 2 transpose, and then V2 2 1. And you know that transpose of a column matrix is actually a row matrix, you know this, and 2 1. Now you multiply them. Please note that, Hadid, what will be the order of the product matrix? When you multiply these two matrices, what will be the order of the product matrix?
2 cross 1.
1 cross 1, good. Because it has order 1 cross 2, it has order 2 cross 1, so this 2 and 2 will be cancelled and the order will be 1 cross 1, right? Okay, so you know this, that's good, and now you are going to multiply them. You already make a structure like 1 cross 1, you multiply like this, 1 into 2 is 2, and minus 2 into 1 is minus 2, so that minus 2, that gives you what? That gives you 0 actually 0, number 0, and this number 0 is a 0 matrix. I will write it as bold 0 like this, dark 0. Oh, null matrix, null matrix. So this is a beautiful property which always hold between two eigenvectors of a symmetric matrix. Note that this is only true for symmetric matrix, right? And I will write that property in red color, and this is a remark. That remark is the eigenvectors corresponding to distinct eigenvalues are orthogonal. This is called orthogonality, right? If whenever you multiply two vectors like this way, I have multiplied, and you get null matrix, they are said to be orthogonal, right? That is, mathematically you can say that Vi transpose Vj gives you null matrix, right? This is a condition for orthogonality, and this is a remark, and this will always hold, right? For distinct eigenvalues, the corresponding eigenvectors will always be orthogonal, right? Okay, fine, but now still the question is still live. The question was asking you to modify V1 and V2. Still you have not modified, you have just observed something, and that observation was good, will be used in future, right? Okay, now modification. What modification can be done? Now I'm going to modify this modification. And this modification is only done in order to avoid the computation of A inverse. We just want to save our time. Time is very precious. Modification. What modification can be done? See, please pay attention. If you divide V1 by its norm, and now you'll say what is norm. Norm is actually I can say length of a vector, right? Norm is a mathematical word, but length is very a common word, which is which can be understood very easily. Length, right? Length of a vector. You know that what is a vector. If you represent it on a Cartesian plane, then the Length of a vector is actually the length of the arrow pointing from the origin towards that vector, right? Like you do in physics. Okay. And I will ask to Shivam Verma. Shivam, what is the length of the vector if I say there is a vector of xi cap plus yj cap, the vector physics vector xi cap plus yj cap. What is the length of this vector? All of you know this. I've studied this in physics. xi cap plus yj cap. Length of this vector. Magnitude. You call it magnitude also. Huh. Please answer if you remember. Answer is under root of x square plus y square, right? And you can see that this v1 is 1 minus 2. That's why you divided this by this, and that will give you a square root of 5. So that gives you v1, and you call it unit vector. If you please try to remember a few things in physics, basic things in vector in physics. What is a unit vector? A unit vector is a vector when a vector is divided by its magnitude. A cap is equal to vector A divided by magnitude of A. Right? So that's what I have done here. I have just found the magnitude of vector V, and now I'm going to divide it by its magnitude. So that will be giving me unit vector. 1 upon root 5, and the other will be minus 2 upon root 5. Right. This is V1 cap. No problem. हो जाता है ऐसा. चलिए आगे बढ़ते हैं. We will modify V2 now. V1 is modified now. Can you modify V2 similar way? Similarly, V2 cap will be V2 was V2 2 1. It was 2 1 2 1, and it will be divided by its magnitude. Right? You can see that magnitude of V2 is also 2 under root of 2 square plus 1 square. That is also root 5. Coincidentally, both of the magnitudes are same. So first will be 2 by root 5 and 1 by root 5, 1 upon root 5. This is the second eigenvector, and these are modified eigenvectors. I'm just putting a cap here, and that gives you an indication that they are actually modified. Are you getting my point? Now see that. Thus, what will be P? Modal matrix. Modal matrix will be constructed by using these modified eigenvectors and putting them in column like this. 2 by root 5, 1 upon root 5, right? And the good thing about this matrix is that if you find its P inverse, and I will ask you to find its P inverse, observe that, right? Observe that if you find its P inverse, then that will be eventually equal to this thing. See, find how to find the P inverse. Please tell me how to find P inverse of a 2 cross 2 matrix. You just switch these two elements with one another. This will be 1 by root 5, and this will be 1 by root 5, and you change the sign of these elements, right? So that will give you, here you will be having minus sign, and here you will be having plus sign. And do not forget to divide this by its determinant. Fortunately, the determinant will be 1 this time. You know that. If you find the determinant of this matrix, that will be 1. Please try to calculate it. 1 by root 5 plus 5 by root 5. Yeah. 4 by root 5. Is it 1? 1 by 5 plus 4 by 5. Yeah, it is 1. Right. The good thing about this matrix is that its determinant is always 1. It's P modal matrix in this modified case. Right? So this is a P inverse, and this is eventually equal to the P transpose. If you find the transpose of this matrix, that is also the same. So what we have done, we have actually modified your eigenvectors in such a way that P inverse becomes P transpose, and everybody at this age loves to find P transpose. Right? That's why our purpose is done. Right? So we can say that then P inverse AP will be equal to P transpose AP, since you have proved that P inverse equal to P transpose, right? And D equal to this. Now, of course, that will be DIAG lambda 1 comma lambda 2, right? Because you are not doing anything. Actually, you are just plugging P inverse, right? And rather to find P inverse, I should write here that I actually found P transpose. Yeah, it is always true. So it is always true. For symmetric matrix, it is always true.